Hi again, and welcome to another screencast where we're going to take a look at a set of objects that are not vectors, but discover that it has some suspiciously vector-like properties to it. This time we're going to look at a set that is somewhat less familiar than the set of polynomials we saw in the last video. This is going to involve a little calculus, namely the concept of a differential equation. Now recall that a differential equation is just an equation that involves a function and one or more of its derivatives. Here's the example we'll be examining here, y double prime plus 4y equals 0. So this is an equation, but here y is not really a variable that represents a number, but rather it's a function of some other variable x. A solution to this equation would not be a number, but a function whose second derivative plus 4 times the original function equals 0. Here's an example of a solution to this differential equation, y equals cosine 2x. So how do we know this is a solution to the equation? Well, let's do the math on the left side of the equation and just see what we get. We have to check that y double prime plus 4y equals 0. So let's calculate each of those things individually. Well, y prime is negative 2 sine 2x because of basic trig derivatives and the chain rule. So that means that y double prime is negative 4 cosine 2x. Now y is the original function, y equals cosine 2x, so 4y is 4 cosine 2x. And so finally, if you add y double prime and 4y together, you get negative 4 cosine 2x plus 4 cosine 2x, which is in fact 0. And so since that function y equals cosine 2x satisfies the equation in this way, it's a solution to the differential equation. Now there are many more potential solutions for this equation as well. For example, y equals sine 2x is also a solution. This is because y prime is 2 cosine 2x, and so y double prime is negative 4 sine 2x, and therefore y double prime plus 4y is 0 again. Also, y equals 5 sine 2x is a solution because of the work you see here. Y double prime plus 4y does indeed equal 0. And another much more basic solution is the constant function y equals 0. Pretty clearly y prime is 0 and y double prime is also 0, so y double prime plus 4y is 0. A function that is not a solution to this differential equation is y equals just cosine x. This is because y double prime is negative cosine x, which you can check on your own if you need to, and so therefore y double prime plus 4y is negative cosine x plus 4 cosine x, and that's 3 cosine x, and that is not equal to 0. So y equals cosine x is not a solution to the differential equation. So as you might guess, there are many solutions to this single differential equation here that look quite different from each other. Let's let S be the set that contains all of them. Now we have no idea what exactly is in S. We have a few examples of members of S, but nowhere near a complete description of this set. Now what would be useful is to somehow get a complete description of S. That would be useful because this differential equation does show up in real-world applications in physics and engineering, and it would be nice to know what its solutions are. We can actually begin to do this if we notice something, namely that although the functions that solve this differential equation aren't vectors, they have surprising similarities to vectors that mirror the similarities that polynomials have with vectors. First of all, notice that S is closed under addition. That is, if I take any two functions that solve the differential equation, then their sum is another function that also solves the differential equation. To see this, let's let f and g be any two functions in S. So we know that f and g solve the differential equation, and that means that f double prime plus 4f equals 0, and g double prime plus 4g equals 0. We want to show that f plus g solves the differential equation as well. So first of all, what's the second derivative of f plus g? Well, from basic calculus, we know that the derivative of a sum is the sum of the derivatives. So the first derivative of f plus g is just f prime plus g prime. And so the second derivative is f double prime plus g double prime. And so now what is 4 times f plus g? Well, we can distribute the 4 to get 4 times the quantity f plus g equals 4f plus 4g. So let's put this all together. F plus g double prime plus 4 quantity f plus g is f double prime plus g double prime plus 4f plus 4g. Moving the terms around gives me f double prime plus 4f plus g double prime plus 4g, and each pair in this last expression is 0 by assumption. So the whole thing is 0. So that means I can take any two solutions to y double prime plus 4y equals 0 and add them to get a new solution. For example, I know without having to calculate anything that cosine 2x plus 5 sine 2x will be a solution to the differential equation. And that's because I know that cosine 2x is a solution, and so is 5 plus sine 2x, and now I know that the set of solutions is closed under addition. So I know that S is closed under addition, but it's also closed under scalar multiplication. That means if I take any solution to the differential equation and multiply by a real number, I'm going to get another solution to the differential equation. Now this makes sense because when I take the derivative of a constant times a function that we learned back in Calc 1, I can factor out the constant. So I can use this to say that, for example, negative 22 times cosine 2x is also a solution to this differential equation because cosine 2x is. And so would 10 cosine 2x minus 3 sine 2x, because I know that cosine 2x and sine 2x are individually solutions to the differential equation. Multiplying each by a constant won't change that, and then adding them together, or in this case subtracting them from each other, won't change either. So you see what I'm doing here is I'm forming what we might consider to be a quote-unquote linear combination of two known solutions to get another solution. Now, so far, this set S of solutions to the differential equation has had the same vector-like properties that P sub n, our set of polynomials of degree of most n from the previous video, also had. And so this set of solutions to the differential equation also has this third property that we mentioned in the last video. There's an element in the set that behaves like the zero vector, namely the constant function f of x equals 0. We already saw that this function is actually in S because f double prime is 0 and 4f is 0, and so adding them together will give me 0 as well. So this function behaves like the zero vector in the sense that when I add it to another function, I get that function back, and that's from basic function properties. So again, we have encountered a set of objects that are not vectors but have surprisingly vector-like properties. So we have to ask ourselves, can we do quote-unquote linear algebra with these objects in any meaningful sense? So we will reveal that answer later. Stay tuned.